swatch. I remember doing these as a kid. Probably saw them too, maybe at a science center or something. Anyway, they're pretty cool. And it happens that due to the way genetics works, the color blindness gene is sex-linked. So it's more likely that you're colorblind if you're male, in other words. Okay, so we have this two-step process where we can map it out using a decision tree, something, well, we call a probability tree anyway, which does the whole experiment. It actually is a duplication of this code that's written over here. Okay, so we flip a coin, and if it's male, then we flip a biased coin that turns up colorblind at 8%, or if it's not male, then it's colorblind at 0.5%. Okay, so an experiment is a block of code. It's adjunct. Okay, so it's equivalent to some probability tree, and we're going to use these a lot in the coming examples, and you should use them too. There's going to be a four-step method, which I'm going to go through today, and you should adopt that method because, sometimes things are confusing. It might not be confusing to you, okay? You might be totally fine, but my experience tells me I get confused sometimes, so maybe some of you might as well. So I highly recommend you do that. Anyway, we'll get to that a little bit later. A couple other definitions just to remind you what's going on. An outcome is any leaf in the tree. And the probability of those outcomes is just the product of all of the probabilities along the arms. Okay, and since we don't have probabilities anywhere between, there are no zero probabilities anyway. We're never going to multiply by zero. Okay, so we end up with this probability tree down here, and we're asked some questions. And the questions that I had up here to start with. Okay, what's the sample space of this experiment? Okay, so just to recall the definitions from the beginning. Okay, so every outcome is a leaf in the tree. Okay, so there are 4 leaves in this tree. They all happen to be on the same level. It doesn't have to be, okay, but I've annotated them as ordered pairs, female not colorblind, female colorblind, male not colorblind, male colorblind. Okay, or if you want to do it in computer code, right, each of these is true or false, right? So you could have done this as like 0, 0, 0, 1, 1, 0, and 1, 1. Okay, so each of those will have some sort of name associated to it, okay? Okay, so the sample space of this experiment, we can list it off in either way. I'll do it the original way so that we don't have to add too much more stuff. Okay, so just in no particular order, but the one along the bottom, right, because it's just a set. You can write it in any order you want. Female colorblind, male not colorblind, and male colorblind. 4 outcomes corresponding to each of 4 leaves. Okay, what's the probability of each outcome? We can do that as well, okay, by multiplying, half times 0.995, a half time. Okay, so each of these has an outcome, all right, so, has a probability, all right, so there'll be 4 lines here. Probability of female not colorblind is, okay, so it's 1/2 times 0.995. Okay, and I'll just set up the calculations here so that we do all the things in a big batch. Okay, so half times 0.005. Probability of male not colorblind is 1/2 times 0.92, and the probability of male colorblind is 1/2 times 0.08. I'll give you a moment to catch up. Okay, so it's just a matter of calculating each of these things. So this is going to be a little less than 50%. This is going to be 0.4975, and this is half a percent. That would be 1/4%, so 0.0025. And this is half of 92%. That's 46%. Pretty easy. And half of 8% is 4%. Okay, so that's just following the definitions from the example. What's the probability of red-green colorblindness? Okay, so we are just doing the same things we've always done, all right? We define what an event is, right, what the event is. This is going to be event B, and event B has 2 possible outcomes. Maybe I'll do a different color than blue up here just to make it clear. There's color blindness on this outcome here, and there's color blindness on this outcome here. Okay, so those 2 outcomes are going to be in B. Okay, so the set containing female colorblind and male colorblind is the set that we're after. And yeah, so we just add them up, just as we normally would. Okay, so that's 0.0025 plus 0.04, so that's 0.0425. And just to take a moment for you to, hone your intuition, probably you suspected it was 4.25%, right? Because, there's half male, half female, right? So this is actually like a weighted average of the 2 things, right? It's 8% likely for a male and 0.5% for a female, right? So average those 2 things out. And indeed, that's what's going on here. but there's another formula for that later on, because sometimes it's not 50-50. Okay, okay, any questions about this? Okay. Does it feel okay? Okay, we're going to spend the rest of today introducing something called conditional probability. And conditional probability basically adds, it does what it sounds like, it adds an extra condition, adds extra information onto a probability. Okay, so this will adjust the probability from when you have no information, and so it should. The more information you have, the better your estimate should be, right? Okay, so how do you see problems like this? You'll see some extra characteristics, some extra information. It's usually, said like an if. Okay, so, what is the characteristic of the dice if you know there's a 4 among the dice, or if you can exclude some possibilities like isn't male, okay? So as an example, we're going to do something, to do with whatever parts, okay? So defective parts, and they're defective in 3, or non-defective in 3 different ways. Okay, and there are 40 parts in the bin, and we pick one at random. 5 of them are just defective. They don't work when you plug them in. Okay, so it's sort of like a light bulb. Imagine you're plugging in a replacement light bulb, you just don't light up. 10 of them will work for a little bit of time, but then they'll fail, like after a couple of hours. And 25 will just work. Okay, so you have, initially your probability of picking a good transistor, a good light bulb that's going to last, is 25 out of the total of 40, right? It's around 5/8. But what is the probability that you pick one out if, when you plug it in, it doesn't fail immediately? Okay, so this is the extra information. Okay, so this I'll just underline with a nice blue swatch. So if it doesn't fail immediately, what's the chances that it's never going to fail? Okay, so this adds some extra juice in there. Okay, and here's how we solve this problem. All right, first we let A be the event that the randomly chosen transistor is acceptable, and there are 25 out of 25 possibilities. Okay, so in event diagram, this A set is the good set that's got 25. B is the event the transistor isn't defective. Okay, and if you look at what's in set B, there are 5 less things, right? It's almost like we took this blue marker, like this. If this goes away, right? There are no 5 things left. Okay, in my diagram that I tend to do, I tend to black out the entire thing. It makes it really unreadable. So I'm just going to try this marker and see if it works. Okay, so by looking at the condition of B, we're basically looking into that window in the sample space now. Okay, there are things that are not included, and it's whatever I just shaded pink. And again, normally I take a big, thick magic marker, black, and black it all out, because this can't happen anymore, right? We know that this can't exist. Okay, so essentially we're changing the sample space. Okay, so that's what we're doing here, essentially changing the sample space. Okay, so the size of A is 25. The size of B is not defective. Okay, the size of A hasn't changed. Okay, but we're now looking at 25 out of 35 instead of 25 out of 40. Okay, so your chances go up intuitively. And why? Because we essentially changed the sample space. We're now looking at this bit here. Okay, so what portion of blue is in there? Okay, so B is the new sample space. That is, we know a randomly selected transistor cannot be defective. Okay, so now it's reduced the problem space down to that of out of 35. Okay, so the problem reduces to selecting 25 acceptable out of a bin of 35 transistors. And we write, and this is the notation, the probability of A, and there's a vertical bar, B, okay, and we read this as the probability of A given B. That's the one I'm going to use the most. Sometimes it's also read as probability of A if B. Okay, and if it feels like, this is like a such-that bar, just like we did the set theory, it actually has the same sort of effect. Okay, so it's like an extra condition on this event A. Anyway, that's 25 out of 35, which is 5/7. Okay, so just to review, we had a collection of 40 things initially, 5 defective, 10 partially defective, 25 acceptable, but we add the condition if. Okay, so if we know that it's not defective, those things go off the table, and we can refine our probability estimate with that extra information. Okay, and it happened to go up here. Okay, sometimes it goes down. Okay, good. Okay, so this is conditional probability. Okay, adding in an if. Okay, so definition. Let A and B be events where the probability of B is non-zero, and we'll see why that is in a second. Okay, then the conditional probability, and it's written the probability of A with this bar B, and it's read as A given B or A if B, is a probability of event A when the sample space is B instead of S. Okay, so we change the sample space, and here I've blacked it out in a more nice way so that it doesn't actually ruin the diagram. So now you're restricted to this area, and that area happens, whatever the surviving bit is whatever intersects with A. Okay, so that's the intuition here. Okay, so that's the intuition behind this formula. Okay, so you're taking all the probability that survives in B, that's the probability of A intersect B when these things both happen, and divide it by the probability of B happening. Okay, and it's the ratio, or it's the fraction of probability that survives. Okay, and this is why there's some. Well, first of all, this is why the probability can't be zero, because you don't want to have division by zero. And also, when we divide by the probability of B, it's not 1 anymore, right? Because it's a new sample space. So we're actually scaling it up to whatever the fraction is, and that makes intuitive sense, right? And in terms of the transistors, the whole space was now 35. In terms of probability, the whole space will now be a new sort of 1. Okay, so it would end up being 7/8 in the previous one, but that's going to be the new total 1. Okay, we're going to redo that example, but we're going to redo it with probabilities. We did that example with the transistors using counts of things. Okay, just counts of good parts or bad parts. Typically, you don't do that, right? Typically, you're dealing with just the probabilities themselves as fractions. So we're going to do that. Okay. Okay. So here's an equivalent version of that example. All right. Defective is 1 out of 8, which is 5/40ths, right? So it's 1 over 8. Defective is 10 out of 40. That should be a quarter, and the rest 25 out of 40. That gives us 5/8. Okay, if we look at the Venn diagram, actually we can put numbers in here. Let's quickly do that. Yeah, okay. So let's see. Good parts, acceptable, 5/8, is in both A and B. Okay, so that region there, A intersect B, should be 5/8. Acceptable or partially defective is all of B. So this region that's out here is not acceptable. It's not in A, but it's outside of A, but in B is 1/4. And we have 1/8, where should that go? Let's see, it's not in A, and it's not in B, so that'll be outside here. Okay, and this region here is empty. Actually, A is a subset of B, as it turns out. It doesn't have to be that way, okay, but it is in this example. Okay, so this is the lay of the land. Anyway, we're going to redo this problem. Okay, redo this problem using the formula from the previous page. Okay, so same definitions. Okay, so let A be the event. The selected transistor is acceptable. And let B be the event, it's not defective. Okay, when I say it's not defective, I mean it's either partially defective or acceptable. Okay, so then the probability of A given B, we're just going to use the formula here. Okay, this is the probability of A intersect B over the probability of B. Okay, so the previous one we used counts. Okay, so we're taking a denominator over 40, a denominator out of 35. That's the transformation here. We're going to take a total of the probability for B as 5/8 plus 1/4, just looking at the Venn diagram. But that makes sense, right? It's either partially defective or acceptable. Okay, with a quarter plus 5/8. And the probability of A and B, okay, it's either acceptable or defective. They overlap entirely, right? So this is going to be just the 5/8 that's there. Okay, so 5/8 on the numerator, 5/8 plus a quarter on the denominator. And 5/8 plus a quarter, well, a quarter is 2/8, so that's 7/8. So I'll put in an extra step. And the 8s cancel out, we got 5/7. Okay. All right. So far, so good? Yeah? Okay, so I'm going to show you the 4-step method, and then the rest of today we're just going to do some practice problems, okay? And that'll be it. Okay, so what's the 4-step method? Okay, and this is taken out of one of your textbooks. I think it's LLM. Anyway, it's really good. I do fall back on this whenever I get confused in an example. And if you find yourself getting confused, it happens a lot with conditional probability. Please use this method. Okay, so it's just turn the crank. Just turn the crank. Okay, so what are the steps? First, you draw a probability tree. Okay, list out all the outcomes. Usually there's a finite number of outcomes. Sometimes there's not. Okay, but you should be able to pick out where the outcomes are as the leaves of the tree. Okay, and writing out a block of randomized code could be a good first step as well. All right. Anyway, so find the sample space and then look at the things that are of interest to you. Okay, so one of them may be, the event of interest, like who wins, or who's colorblind, or whatever. And then there's a condition, like which team has an advantage, which gender you are, this sort of thing. Okay, so there are usually going to be two of these things that you're going to combine, and then map them out. Okay, so count the ones that overlap, and find their probabilities. Okay, so and you'll take a product. Okay, product along the edges of its path. This follows the multiplicative rule, where you multiply everything along the edges of, along the way to the leaf. Okay, and whatever happens to be in B, you add all that up. That's going to be your denominator. And wherever A and B happen to overlap, that's going to be your numerator. And you just sub it into your equation, and you're done. Okay, so even if you have no intuition, or maybe it runs counter to your intuition, that happens a lot. Okay, it doesn't seem to make a lot of sense. Generally speaking, you can fall back on this. Okay, so, yeah, let's do an example. And some of the examples that we do have been like mind trap examples in other, some magazines, some newspapers, some math textbooks. I've kind of reduced the trickiness down so that we can solve the problem and it doesn't have like this ambiguity, but you might find different versions of this problem, also the Monty Hall problem, which we'll do on Monday. So just be warned that the wording here is just slightly different. Okay, so I'm not trying to trick you, but just challenge your intuition a little bit. Anyway, there's a father-son gathering at Jones's work, and he's been invited. Okay, been invited to go with his youngest son. So the question is, what's the chances that Jones has two boys? Okay, given that he has two children. Okay, let's follow the method. All right, so the method is, find the sample space. To do that, it might be helpful to write out some computer code. Let's do the computer code. Okay, so computer code here. Jones has two children. So first boy equals Bernoulli of a half, and second boy equals Bernoulli of a half. I know biology is a little bit more complicated than this, but we'll just go with 50-50. Okay, and we end up getting a probability tree. Okay, so 50-50, girl, boy, and then second child, again 50-50, girl, boy. Okay, so either side, girl, boy. And in terms of ordered pairs, we could do zeros and ones. I'm going to do G's and B's. Okay, so this is GG, WP, GB, BG, and BB. Okay, so this represents the experiment and the sample space. I'm not going to circle them because I don't want this to get too messy, but there are 4 possible outcomes in the sample space. Okay, so assume the sample space is these 4 items, 4 ordered pairs. Okay, and it's just the G's and B's in permuted in any order. Okay, 4 different things. Okay, so that's step 1. Okay, step 2, define events of interest. All right, question? Yeah, so how is girl-girl possibility? It just is a possibility in life, right? That if he has 2 children, it could be girl-girl. The question that you're kind of getting at here is the event that, he's got at least 1 boy. Okay, and that's not possible. Sorry, it's not possible that he doesn't have, girl-girl for that event. Okay, so that's the defining events of interest. That's going to be on the next step. And we're going to exclude that possibility. Because if you have 2 children, it's, assuming these events are independent, it's 50-50 all the time, right? So a quarter of the time he would have 2 children, they would be both girls, right? Okay, but we're going to exclude that on the next step. Yeah. Okay, so let's do that. Okay, events of interest. Okay, so we're interested in, let's see, what's the probability that they are both boys? Okay, so both boys, we'll say is A. Given that he is invited to the dinner means he has at least 1 boy. This is going to be B. Okay, so the event we care about is Jones has 2 boys. So that'll be A, and that's just going to have BB in it. And the additional information, okay, so let's just annotate that in the diagram real quick. So A is just this outcome down here in the bottom right. Okay, so that's all of A. Additional info is that Jones has at least 1 son. So B is going to have these 3 outcomes, okay? GB, BG, and BB. Okay, and in terms of, all of them being collected, I don't want to put down 3 Bs, but we can do it using like a Venn diagram-like thing. We'll just kind of collect them all, something like that. Okay, so we're just reading the problem. All right, so we want A given B, and to do that we need A intersect B and B. Well, A completely intersects B, so that's easy. So it's just the probability of A. And the probability of B, okay, so we need the probabilities of each of these. And that's a half times a half for all of them, right? So it's a half times a half equals a quarter. It's a quarter for all of them, right? Okay, so we need probability of A intersect B. That's equal to, well, I guess the probability of, okay, so they completely overlap. So this is the probability of A, which is a quarter. And the probability of A is a quarter plus a quarter plus a quarter. So that's 3 quarters. And the probability of A, that he has 2 boys, given the fact that we know he's got at least 1 boy, is the probability of A intersect B, or the probability of B. So we just divide a quarter by 3 quarters, and we get a third. Okay, so if we didn't have that information, that extra information, the probability that Jones has 2 boys is a quarter, right? And he's got to win 2 coin flips to get 2 boys, right? So it's 1 quarter. Here it's gone up, okay, because we have extra information that he doesn't have 2 girls. Kind of cool. Okay, questions about this one? Yeah, does it feel okay? All right, well, let's do one more, and then I'll show you something interesting on the summary slide. Okay, let's do this hockey example. Okay, so best of 3. Okay, and this is the format of a lot of tournaments, and if you've ever seen little kids play hockey, it's kind of fun. The ice is very big, and they fall down a lot. And they are also very momentum locked. Okay, so if they're winning, they tend to win more, and if they're losing, they tend to lose more. So they, it's kind of fun to watch. It's a very interesting game. And so this is the model, okay, of this problem, that they play tournament, best of 3 tournament. So if you win 2, you win. But if you win 1, or if this team wins 1, then they get momentum. Okay, so the likelihood they win their next game it goes up from 50-50 to 2 out of 3. And if they lose, then they're down on themselves or whatever, and the chances are reduced. They're down to 1/3. Okay, so what's the probability that they win the tournament if they win the first game? There's also a part B here. What's the probability they win their second game given they win the series? Okay, so there's different events that we can condition on. All right, first, let's write a computer program. Okay, so that we know exactly what we're talking about, and we'll draw a tree that works with this. Some of you may just want to draw the tree. That's cool too. Okay, so if it's very clear to you what's happening here, draw the tree. I have no problem with that. Okay, but I'm going to do the computer program. Okay, so we have 2 variables, wins and losses. And the first game is a coin flip. Now, we add 1 to wins if game win is 1. Otherwise, losses go up. And then the tournament doesn't end. There's always going to be a second game and possibly a third. Okay, so, and you can extend this. The reason I'm writing the code this way is that you can extend it to a best of 5 or best of 7 if that's what you want to do. And indeed, a problem, maybe 2 on your coming assignment will have something that will be like a best of 5. Anyway, while we don't have 2 wins and we don't have 2 losses, we keep on flipping biased coins, okay? And the way that we flip biased coins is based on whether or not they won the last game. So if it's a game win, then the next game you win with probability 2/3. Otherwise, you win with probability 1/3. Okay, and then we have this line. I don't know, I'm running a little bit short on time. This line is repeated down here. Okay, so if it's game win, then wins must equal 1, and if otherwise you increase the losses. Okay, so this loop will run at least once, maybe twice. Okay, if you wanted to extend this to best of 5, you'd say less than 3, less than 3. Anyway, some of you just like the probability tree right away. That's fine. Draw it. Okay, so what are we looking at for the drawing of this thing? Okay, so we're going to give it a very wide first go here, because the branches go down more than 2 deep. Okay, and we'll do loss on the left and win on the right. Okay, so if your first game is a win, then your next game is either a win or a loss, 1/3, 2/3. And you keep playing if you've lost 1 and won 1, but the last game is you're more likely to lose, I guess. So that's 2/3, 1/3. And if you win 2, you don't have any arms going off here. Okay, so this is an example of a tree where your outcomes are not all at the same level, right? Okay, so this is it. You win in 2. This took 3 games to win or lose. The symmetric version of the tree is drawn over here, because if you lose 2 in a row, you're out. And if you lose-win, then you're still playing. Okay. So just to annotate the cases, and I'm going to collect them into a sample space in a sec, but this is loss-loss. You can look at them as strings rather than ordered pairs or triples. Loss-win, loss, loss-win, win, win, loss, loss, win, loss, win, and win, win. Okay, so there are 6 outcomes. The sample space is those 6 outcomes. Okay, that took a moment. Define events of interest. What is the probability they win the tournament? Win the tournament is going to be event A. Given that they win the first game, that's going to be event B. Okay. Let A be the event they win. If I was to write A as a set, what would I put in A? Win-win, win-loss-win. Loss-win-win. I get them all? Okay, so A is here, here, and here. Okay, let B be the event they win the first game. Okay, what's in set B? What's in set B? Win-win, win-loss-win. Anything else? Win-loss-loss. Okay, any position where they won the first game. So that's everything that's over here, right? They won the first game. That's B. Okay, so what we're going to do is we're going to collect all of the outcomes that overlap A with B, and there are 2 of them. And each of these has, we can multiply out the probabilities. Okay, so let's just quickly do that. 1/2 times 2/3 is 1/3 for this. 1/2 times 1/3 times 1/3, that's 1/18. And 1/2 times 1/3 times 2/3, that should be 1/3 times, that's 1/9. Okay, and those 3 things should add up to be 1/2 because, this is the whole side of the tree. According to this, right, it's 1/2, right? You won the first game. And indeed, just verify it. 1/3 plus an 18th plus a ninth. So an 18th plus a ninth is 3/18ths, which is a sixth, and a sixth plus a third is a half. Okay, so this win-win is a third, this win-loss-win is an 18th, this win-loss-loss is a ninth, and the events that we're interested in that overlap A are this one and this one. Okay, so the probability of A given B is the probability of A intersect B divided by the probability of B. Okay, so what's A intersect B? It's these two things, so it's a third plus an 18th. The denominator I've already added up to be a half using my shortcut observation, but if you have no observation, that's okay. You can just add those fractions, no problem. So the denominator ends up being a half. Numerator, how many is that? That's 7/18ths. Okay, so we'll rewrite this as 18ths so that they get some nice cancellation here, and this is 7/9. Okay, so if they win the first game, they are pretty likely to win the whole thing. That's sort of a good intuitive thing, right? It seems to gel with their intuition anyway. Okay, questions about this part A? Yeah, is it okay? All right, part B. What's the probability they win their second game, given they win the series? Okay, so win the series is A. Okay, so we've already got A here, okay, is WWW, LWW. And win their second game, we'll need another event. We'll just call it C. So let C be the event they win their second game. C, sorry, thank you. Trying to keep all the things in play here, but it's proving to be a little difficult. Okay, so C, they won their second game. Okay, so we just go and collect all the things where they won the second game. So LWL is one of them, LWW, and WW. Okay, and the ones where they overlap with A, let's just go back up here, we don't need the diagram anymore, are, let's see, WW is one of them, and LWW. I guess we might need the diagram for some small things here. Let's see, LWL is a half times a third, so that's 1/18th. This is LWW, that's 1/9, and WW is 1/3. I guess we didn't need 1/18th. All right, so we just apply the formula again. Okay, but this time we're conditioning on A. That's perfectly fine. Okay, so the places where C overlaps A are these two outcomes. That's 1/9 plus 1/3. And the probability of A, okay, so that's WW is 1/3, and LW is 1/18th, and LWW is 1/3. Did I do that right? Oh, LWW is 1/9. Okay. Oh, sorry, that one. Sorry, LWW is the last one. Okay, so I sort of muffed that. Let's just rewrite that. Okay, so that's the denominator. Is that right? Okay, so they win the tournament. Well, that's actually a half. That's kind of cool. Okay, and that sort of matches our intuition because this tree is symmetric. They win the tournament 50% of the time. 1/9 plus 1/3.